In the previous semester, we explored an article that highlighted humanity's reluctance to confront the root causes of problems, especially in the context of biological systems. One striking example was the overuse of pesticides in the 1940s to 1950s, which temporarily solved pest problems but led to resistance, ecological damage, and unintended consequences. Despite decades of scientific progress, the same tendency persists today. We often apply technological fixes before fully understanding biological complexity. In this debate, we examine the legitimacy of such approaches in two contrasting areas: traditional Korean medicine, as known as TKM, and modern biological systems, such as genetic engineering or synthetic biology. We aim to present arguments for and against the application of technology in both fields, evaluating whether partial knowledge can justify real-world implementation. First, TKM issue explained. Traditional Korean medicine, or TKM, is a holistic medical system with a long-standing clinical tradition grounded in theories of balance, such as yin and yang, the five elements, and constitutional typologies like Sasang medicine. Treatments are deeply individualized, emphasizing the relationship between physical symptoms, emotional states, and a person's overall constitution. In recent years, modern technologies such as EEG, network pharmacology, and AI-assisted diagnosis have been introduced to study or enhance TKM. These tools aim to quantify effects, identify biological mechanisms, or standardize diagnostics. The issue whether it is justifiable to apply these technologies to TKM with both sides' traditional medical theory and modern tools are not yet fully understood in relation to each other. Proponents argue that technological integration, even if partial, can support clinical usefulness and expand accessibility. Opponents argue that premature application risks distorting TKM logic, misinterpreting its effects, and forcing it into a biomedical framework that may not align with its foundations.
Speaking in the proponent side of the thesis, in real-world medicine, action often has to come before full explanation. This is not unique to traditional systems. In modern psychiatry, for example, we routinely prescribe medications such as antidepressants and antipsychotics without fully understanding how they work. Lithium, used as a first-line treatment for bipolar disorder, is a case in this point. It has proven life-saving effects in mood stabilization and suicide prevention, yet its mechanism is still debated. Despite this, we use it, because the need is urgent and the clinical outcomes are clear. The same approach can and should be applied to traditional Korean medicine. Many TKM treatments for conditions like anxiety, insomnia, or emotional imbalance have been used safely and effectively for centuries. While modern scientific methods may not yet fully validate them, patients still report significant relief. Especially for individuals who avoid psychiatric care due to stigma, side effect concerns, or cultural barriers, TKM provides a meaningful and accessible alternative. Moreover, technologies like EEG, HRV monitoring, and network pharmacology often partial evidence that helps us understand how these treatments affect the body. We can observe changes in brain activity, stress responses, and even neurotransmitter levels. This may not fully capture the traditional reasoning behind the treatment, but it helps bridge the gap between traditional knowledge and modern science. In both psychiatric medicine and TKM, what matters most is clinical benefit, especially when the risks are low. Waiting for perfect knowledge may sound scientific, but in reality, it delays help to people who need it now. Just as psychiatry continues to apply partially understood tools out of ethical responsibility, so should we apply modern technology to support and expand TKM carefully but without paralysis.
Well, speaking in the opponent side of the thesis, the idea of using modern technology to support traditional Korean medicine sounds progressive. But when we look closely, it raises serious concerns. The biggest problem is not the technology itself, but the lack of deep understanding on both sides. TKM is a coherent, internally consistent system built on its own theoretical foundation. Concepts like ki, yin-yang balance, organ systems correspondence, and Sasan constitutional types. These are not just poetic metaphors, they are clinical framework that guides diagnosis and treatment. Attempting to interpret them through biomedical tools without first fully grasping their internal meaning risks distorting them. Likewise, the modern technologies often introduced, like EEG, HRV, AI-based pulse readers, or network pharmacology, come from a completely different paradigm. They measure things like brainwave frequencies, etc. But these measurements don't naturally align with the logic of TKM. A spike in alpha brainwaves, for example, tells us something about nervous system activity, but it does not necessarily map onto TKM's understanding of what this term liver system or excess am. So, when we say that technology is validating TKM, we must ask, validating what and by whose standards? Does it really align with the TKM's perspective on looking at the human body? There's also a structural risk. Many modern tools, especially AI, are built to identify patterns based on large data sets. But TKM emphasizes individual variation. Two patients with the same symptoms may receive different herbal formulas based on their constitution, emotional states, or pulse pattern. If we try to train AI models on simplified symptom to treatment parents, we lose that flexibility. In doing so, we risk turning TKM into a generic protocol rather than a personalized medical art. What meant to is increased credibility could end up hollowing out what makes TKM effective and its self-meaning. Finally, and most importantly, the solution isn't to reject technology altogether, but the process in the right order. It's a process. TKM must first be studied, preserved, and understood in its own terms, using both traditional scholarship and reflective clinical observation. Only then can we explore meaningful points of connection with modern tools. Otherwise, we're not integrating knowledge. We're imposing one model on another under the illusion of progress. In short, applying modern technology to TKM without deep dual understanding may look like innovation, but it can actually lead to oversimplification, misalignment, and cultural erasure. That is not a risk we should take lightly. Thank you.
Biological system issue explained. As science and technology continues to evolve, humanity increasingly relies on applied innovations to solve pressing global challenges. From eradicating diseases and increasing food production to developing sustainable industries and environmental management strategies, applied science plays a vital role in improving human life. However, the application of scientific knowledge, particularly in complex biological systems, comes with significant ethical and practical concerns, especially when full understanding is lacking. Scientific progress is rarely based on complete certainty. Technologies such as mRNA vaccines, CRISPR gene editing, and AI-based diagnostics continue to be developed and deployed even as researchers work to fully understand their mechanisms and long-term effects. Supporters argue that responsible regulated application backed by sound evidence and can address urgent issues like pandemics, genetic disorders, and global food insecurity. Critics, however, caution against the risk of unforeseen harm, emphasizing past mistakes of DDT or PFAS as cautionary tales. This debate confronts a central tension in modern science. Should technologies be applied if our understanding is incomplete? Or should we wait for greater certainty even when human suffering or planetary crisis escalate?
Speaking of the proponent side of the thesis, while the complete understanding of complex biological systems may be ideal, delaying technological advancement until such an understanding is achieved is neither practical nor ethical. In urgent and evolving fields such as public health, agriculture, and genetics, the responsible application of emerging technologies, even under partial understanding, is not only justifiable, but often necessary to address global crises. Scientific discovery often unfolds ahead of complete theoretical confirmation. For example, quantum mechanics, still not fully understood in philosophical or physical terms, forms the basis of modern semiconductor devices, enabling advances in computing, data storage, and telecommunications. Similarly, technologies such as mRNA vaccines and CRISPR gene editing tools were fast-tracked during global challenges like the COVID-19 pandemic and the rise of rare genetic diseases. Though long-term consequences are still being studied, their immediate benefits have been undeniable. mRNA vaccines save millions of lives globally, and CRISPR has offered possible cures for previously untreatable conditions like sickle cell anemia. Moreover, modern regulatory agencies such as FDA or EMA incorporate rigorous multi-phase testing frameworks to minimize risk. Computational modeling, artificial intelligence, and big data tools increasingly allow scientists to predict toxicity, efficiency, and systemic effects with greater accuracy than before. Historically, science has progressed through iterative processes, experimentations, error, and refinement. Waiting for perfect understanding would have stalled every major scientific breakthrough. In an era defined by climate change, pandemics, and food insecurity, the risk of inaction might outweigh the risks of imperfect application. With ethical oversight, transparency, and adaptability built into regulatory systems, applied science enables both innovation and safety. Thus, applying emerging technologies under responsible constraints is not reckless. It is a rational and necessary response to an urgent and imperfect world.
Speaking in the opponent side of the thesis, the application of synthetic chemicals without a comprehensive understanding of their long-term impacts on biological systems has historically led to significant and often irreversible damage. This reinforces the need for scientific restraint and humility before implementing widespread technological solutions. Biological systems are deeply interconnected and inherently complex, meaning that even small interventions can lead to disproportionate and unpredictable outcomes. This has been demonstrated in the case of DDT, as synthetic pesticides developed in the late 19th century but widely used after World War II for pest control and to combat vector-borne diseases like malaria. Initially, DDT was celebrated for its effectiveness, with early toxicological assessments suggesting it was safe for human exposure under controlled conditions. However, extensive use led to the compound entering ecosystems through agricultural runoff and atmospheric deposition. It was later discovered to persist in soil and water for decades and to bioaccumulate in the fatty tissues of animals. DDT disrupted avian reproduction by thinning eggshells, causing drastic population declines in species such as the bald eagle and brown pelican. These discoveries prompted widespread concern and ultimately led to its ban in many countries by the 1970s. A contemporary parallel can be seen with PFAS, a group of man-made chemicals used since the 1940s in a wide range of industrial and consumer products, including non-stick cookware, firefighting foams, and waterproof clothing. Often referred to as forever chemicals due to their resistance to environmental degradation, PFAS compounds have been found in groundwater, soil, and even the bloodstreams of humans and wildlife. Emerging research links PFAS exposure to health problems such as hormone disruption, liver damage, immune system suppression, and cancer. Yet, these chemicals remain in use due to their unique functional properties. Like DDT, PFAS were initially seen as technological advancements, but are now recognized as environmental threats with global reach and long-term implications. When evaluating technological solutions, especially those involving widespread chemical deployment, it is essential to consider the historical pattern they follow. Initial enthusiasm based on short-term benefits, followed by limited safety testing largely from a human-centric view, culminating in broad adoption, and finally the emergence of serious environmental and health consequences. This cycle illustrates a systemic failure to anticipate how human activities interact with the complexities of ecological systems. Overconfidence in our scientific models, many of which cannot fully capture ecological interdependencies, often leads to unacceptable risks. The cases of DDT and PFAS affirm the necessity of adopting the precautionary principle. Solutions should not be deployed on a large scale until their long-term environmental and health impacts are thoroughly understood. Technological progress should proceed with humility, acknowledging our limitations in predicting the consequences of introducing persistent synthetic compounds into ecosystems. In a world where our actions can have unanticipated and far-reaching impacts, scientific precautions must serve as a cornerstone of policy and innovation. The legacy of DDT and the growing crisis surrounding PFAS provide sobering lessons. That the promise of new technology must never overshadow our responsibility to safeguard living systems. Proceeding without full understanding is not only scientifically negligent, it is ethically indefensible. In conclusion, applying technology without fully understanding can be justifiable in urgent cases, such as psychiatric care or pandemics, where waiting may cause greater harm. Similarly, using modern tools like EEG or AI in traditional Korean medicine can help expand access and other partial validation. However, history warns us through cases like DDT and PFAS that hasty application often leads to long-term damage. TKM, with its unique logic and personalized approach, risks being misrepresented and forced into a modern mold too quickly. In both biological science and TKM, we must balance action with caution, innovation with humility, and urgency with deep respect for complexity.